Good thing. So, inductance. All of these things that we've learned so far about the induced current in wires due to changing magnetic fields and conductors due to the induced current in conductors in general due to changing magnetic fields around them because of the changing magnetic flux and everything. All of this stuff has a lot of uses. We've already seen one with the transformer. We've also seen one with, the generator and the motor. Those are useful things that are all kind of related to these ideas. And now we're going to look at another one, which is called the inductor. So let's look at an interesting situation that we got going here. We've got two coils sitting next to each other, and the first one is we're causing a AC current to be driven through this coil. So back and forth through this coil, back and forth. That's what this little symbol is down here for AC. This is an AC generator, and it's creating a current back and forth through this coil, which of course is going to create a magnetic field through this coil, right? The magnetic field will change when the current is going the direction they're showing right now. It will be pointing to the right, so the north pole of this magnetic field would be over here. And when the current changes the other direction, it will go the other direction, so it's constantly changing back and forth. The second coil is connected to just a current meter. So we're just measuring the current or the voltage over here, whatever this meter is set up to measure. It looks like it's set up to measure the voltage. And it's seeing or detecting this magnetic field as it changes. As it changes through here, you're going to get a changing voltage going back and forth over here. But that detection is happening because of an induced current in this coil over here. This coil over here, when it has an induced current, it will create a magnetic field. And that magnetic field will be felt by this coil over here, which will change the current in this coil over here, which will create a magnetic field in this coil over here, which will create a changing magnetic field for this coil, which will change the current in this coil, which will change the magnetic field over here, which will create a new... It goes back and forth and back and forth. So whenever you create a current in a coil that creates a magnetic field that affects some other coil nearby, they affect each other back and forth constantly. It's called mutual inductance. They're always inducing currents in each other, and those things are always related to each other. And it can get quite complicated, but it can also be simplified. And this is the result of this simplification. The EMF in the second coil is going to equal the change in current of the first coil over the change in time. So that part right there is like Faraday's law. But we have this factor between them called the mutual inductance. And the mutual inductance is a constant dependent on the coils, dependent on the configuration of the coils. So each pair of coils has a mutual inductance M that is different than other mutual inductances for other coils. The EMF that is in one, that is caused in the first coil by the second coil, is the same. It's the change in current in the second coil divided by the change in time times the mutual inductance between the two coils. And there's that negative sign from Faraday's law again. And this is all done. This is all after a physicist named Joseph Henry that figured this all out. So the symmetry back and forth again kind of gives a little bit of a nod back to Newton again, whose third law suggested such symmetries exist, and we get this interesting thing going on. So here's a very unique, interesting way that this is where this is used in heating coils. So a clothes dryer heating coil. This particular heating coil is wrapped around a core. It can be wrapped around like an iron core to increase this effect. But regardless of whether it's wrapped around a core or not, it's still a loop, and it creates this magnetic field. And this loop is actually not one loop, it's two. what they did is they folded the wire in half so that the current is going in different directions on each side of the wire now. And then they looped that, so it's like having two coils that are intertwined with each other, where the current is always going in opposite directions on every other coil. This is what they call, what do they call this? Counterwound? Yeah, they call it counterwinding. Why would you do that? Well, because when you have two identical coils where the current is always going opposite in each coil, you actually reduce the effect of the self-inductance, or of this mutual inductance. Because if the current is always going in opposite directions, then those two magnetic fields always cancel each other out, and there is no mutual inductance between the two coils. Why would that be a good thing? Well, because inductance causes currents in the opposite directions than you're trying to create the currents. So you want to sometimes cancel that out. So they take advantage of this to get rid of the mutual inductance, or to lessen it considerably. So counterwinding coils is a very interesting application of this idea in this law. But here's another problem with these things. It just gets worse and worse and worse. You have a coil. Let's see if we have a coil here. So let's, I thought they had a, let's see, did they have a demonstration on the last section? I think they did. No, they didn't. That's okay. So for any coil that you have, no matter what kind of coil it is, just any old coil will do. You create a current, put a current through it, drive a current through it that's alternating back and forth. So you have current back, current one way, current the other way. Magnetic field's going one way. When the current's going one way, the magnetic field goes the other way when it changes direction. So the magnetic field's going back and forth. Well, guess what? That magnetic field is going through its own coil that created the magnetic field. And the magnetic field, as it changes going through that coil, actually creates an inductance in the coil. It actually induces its own current inside of itself. So this effect is even true on coils that are creating the magnetic fields. The magnetic fields they create affect the coils themselves. And this is called self-inductance. And the self-inductance, again, has the negative sign, has the delta I over the delta T, but there is, instead of a M in here, we put an L for the self-inductance of that particular coil. Now, to know what M is for mutual inductance to I, or L for self-inductance, you have to either be told that or be able to calculate that from the geometry and the makeup of the coil. In the case of this book, they will mostly give it to us. They'll give us the value of L, or they'll give us the value of M. But in the end, it comes down to flux. Excuse me. Change in flux. And in this particular situation here, they're actually comparing the current to the self-inductance. And when you do that, you can actually solve for the self-inductance as a value of the flux going through, which is going to be the area of the coil. The area of the coil is going to be involved in the flux. Also, the changing magnetic field will be a part of that, but also the number of coils. So they've actually given us a value for the self-inductance, a way to calculate the self-inductance of a coil. If you really get down to it for other things like solenoids, you can be very specific. It has to do with the number of coils per unit length. It has to do with the area, the cross-sectional area of the solenoid, and the length of the solenoid. And so in this example, they actually have us calculate the self-inductance of a solenoid, because we can do it so specifically. They tell us that it has a 4 centimeter diameter, so we can calculate the area. They tell us the length, and they tell us the number of coils that it has. Actually, N is the number of coils, not the number of coils per unit length. I don't remember which one I said, but N, the big N is the number of coils. Little n is the number of coils per unit length. But anyway, we just plug in the numbers into this equation and we will get that, except we do have to calculate the area. The area is going to be half of the diameter, which is 4 centimeters squared times pi. And we also need to convert everything into meters for length and all of that. So we do all of that, and we get 0.632 millihenries, 0.632 times 10 to the minus 3 henries, named after our friend Joseph Henry, for the self-inductance of this coil. So, and here's a great application of this right here, the security gate at an airport. How is the security gate in an airport going to be an inductance thing? Well, it's simple. The security gate has actually just got a big coil of wire on one side of it. Actually, probably on both sides. But it's just got two coils of wire in it, and those coils have current going through them. And when there's nothing going on around them, nobody's moving, nobody's doing anything, then those coils have that current going through them that you've put through them, and they have a self-inductance that is easily measurable, easily determined. However, if you introduce anything that changes the magnetic field between those coils, it changes the self-inductance of the coils, which changes the current going through the coils. So the coils will draw more current. The voltage will go up. So if you're carrying keys, or if you're carrying anything magnetic, anything that has any iron in it at all, for example, or nickel or titanium, or anything that's magnetic, it will trigger that device. Now, what about non-metallic metals? Brass, not non-metallic, non-magnetic metals. Brass, copper, gold. Those are non-magnetic. Will they cause a change in the self-inductance? Yes, because the current that is being driven through these coils is creating a magnetic field inside of this little booth. That magnetic field is changing. It's an AC current. And that changing magnetic field that's going back and forth has the effect of creating a current in any metal at all that you're carrying with you, which will create a changing magnetic field back, which will change the self-inductance of those coils, which will change the voltage across those coils, which will be detected. So it doesn't matter if you're carrying a lot of metal, a little metal, magnetic metal, non-magnetic metal, will detect any kind of metal going through it. So it also can, and then they're saying here that they can also tell about how high they are above the floor. And that can be done in a couple of different ways. It can be done with a computer, which would determine kind of where the change in magnetic field happened. But you can also do it more mechanically by having, instead of one big coil, you can have several sets of smaller coils, so that where the voltage change takes place determines the height of those things above the floor. And that is the actual method that they use, because it's easier, cheaper, and more reliable. So, right here it says they will not be able to detect any plastic explosive such as that found on the underwear bomber. So explosives are sometimes metallic, sometimes not. So you gotta... Yeah, when you have metal in your body, you actually have to declare that when you go into an airport. You have to tell them that. You have to have medical proof that that's in your body. And then usually they will take you aside for essentially for a personal search. Usually you'll get patted down by hand. So, and they will use one of those. So they also have those handheld ones. Those handheld detectors are the same thing essentially, except they actually work by movement rather than by changing the currents through the coil. So the current can be a DC current there, but because they're moving it past objects, it will change the magnetic field will be changing by motional EMF rather than by changing the current. So that's why they have to move those. That's why they wave them around you, because they have to be moving to work. All right. And the easiest way for them to detect that is to hear it. So instead of just looking at the voltage while they're moving it, which would be very difficult to do, right? They actually just connect the little voltage to a speaker so that the voltage causes the current to be driven through the speaker, and then they can hear when metal goes by. So it actually changes the tone. That's why in the movies it always goes, you know, that, because if it's detecting metal, it will make those sounds. If it's not detecting metal, it won't make those sounds. So normally you don't hear any sound, even though in the movie you always hear a sound. Anyway. All right, let's do a, let's see, what did we forget here? Oh, right here. So energy stored in an inductor. What? Where is the energy stored in an inductor? Now, an inductor is essentially just a solenoid. It's just a coil wire that you put into a circuit. And sometimes you put a piece of iron in the middle of the coil to make it a stronger inductor. So it will build a stronger magnetic field. Where is the energy stored when you have an inductor in a circuit? Well, let's think about it. Does a magnetic field have energy? Can a magnetic field cause objects to move? Absolutely. So obviously a magnetic field has energy in it. Okay? When you put a current through an inductor, do you have a magnetic field in the inductor? Yes. When you put a current through an inductor, you create a magnetic field that's going down the middle of that inductor. And that magnetic field is actually stored energy. It's energy that can be used for something. Now, the interesting thing about it is how it is used. With inductors, when you start the current in an inductor, like when you plug in your laptop, you start the current through your inductor because that laptop charger has some coils of wire in it. You start that current through that inductor, and it's just stored in that magnetic field. When you unplug it, that spark that's created is from the energy stored in the inductor. So the inductor stores energy that wants to go in the opposite direction, wants to drive things in the opposite direction, right? And so it's actually part of the self-inductance of the inductor. And it's directly proportional to the square of the current that is going through the inductor, it turns out. So here's the equation for that. That is something that is beyond this class, calculating that equation. It's a calculus thing. But they give it to us here. The energy in an inductor is equal to 1/2 times the self-inductance of an inductor times the current squared through the inductor. So they want us to calculate the energy stored in an inductor that has 30 amps going through it, and it's 0.632 millihenry inductor, has a 0.632 self-inductance. Plug those numbers in and we get 0.284 joules of energy. Okay? So it could cause a spark. Takes time for that to build up. Takes time for it to be used up, but if you force it to turn off really quickly, it'll send all that energy all at once, or as quickly as it can. So now we get to this part where we're going to actually use inductors to store energy in a circuit. And this is how it works. We have a battery, we have a resistor, and we have an inductor all connected in series. But we also have this switch that can be switched back and forth between the circuit with the resistor and the inductor in it, and it can be switched to bypass the battery on this line here. Okay? And what we're going to do is we're going to start by switching it to the battery and letting the battery start to push current through this resistor and through this inductor. And what we notice when we switch this on is that at first there's no current going through the circuit. And then it slowly begins to build up current until it reaches a maximum value, and then it just flattens off and you get that amount of current. So that's what happens when you switch this thing on, connect it to the battery. The current tries to go through this inductor and resistor, but it can't at first. Why can't the battery push the current through that inductor when it first gets turned on? The question really is, what is the magnetic field through the inductor before we turn the battery on? What kind of magnetic fields are going through the inductor before we connect the battery? Is there a magnetic field from the Earth going through there maybe? Possibly. Has it changed much? No. Is there any other changing magnetic field through this inductor before we turn it on? Not likely. So before we turn this on, this inductor is as happy as can be. It doesn't want to see a change. But as soon as we turn on the current, we drive a current through that inductor, and it starts to build a magnetic field that goes right through itself. And do inductors like changes in magnetic field going through them? No. So the inductor will resist the change. And so we don't get very much current when we first turn it on. The inductor actually creates a back EMF which resists the change. And this is the evidence of that back EMF. We turn the switch, we should get 12 volts across or whatever voltage we're supposed to get across it. But the back EMF from the inductor right off is really high, almost equal to the voltage that we switch on. But eventually, as it slowly builds up the current, the inductor slowly changes its back EMF. And it slowly dies off, and then we slowly get current through it. So at first, the change is so big, the inductor fights back really big. But the fight eventually gets won by the battery, and we slowly turn this on. Now, if you have a bigger battery, this change is going to be bigger, and the EMF is going to fight back more. If you have a smaller battery, the change is going to be smaller, and the EMF is going to fight back less. So, but eventually, the current will flow. It just takes time. What's going to happen when you turn this off? When you're about to turn off this thing, the current is flowing through the inductor, so it's got a magnetic field through it because it's creating a magnetic field that goes through itself. Does it want that magnetic field to go away? No. So when you switch it off, the current's not going to go off right away because the inductor is going to force that current to keep going. That's why you get the spark. And so the current doesn't turn off right away. It slowly turns off and then eventually dies off to zero. Where does the energy come from to keep driving this current? We've unplugged it, but the current keeps going for a little while after we unplug it, or after we flip the switch. Where does the energy come from? Where did we store energy in the system? Where did we store? Did we store energy in the resistor? Do resistors store energy? No, they just dissipate energy, right? All resistors do is heat up and turn the energy into the atmosphere. Where did we store it? In what part of the inductor? What did the inductor create that can store energy? Magnetic field, right? So when we started driving current through here, we started storing energy in the magnetic field that we were creating. When we turned it off, the magnetic field had a bunch of energy and it needed to go somewhere, and it went into driving that current around the loops more. So if we switch the switch from the battery to this place, the current will still flow. It will just flow through here, but it eventually dies off as the magnetic field dies off. And then it will go to zero. So this right here is a slow turn off, turn on system. If you want a system to turn on slowly and to turn off slowly, just put an inductor in there. And the size of the inductor will determine the speed of the turn off and turn on in your system. How much inductance it has. More inductance will turn on slower and turn off slower for a given voltage. Here they have an equation that tells you how the current will change over time. Here, this is when you're turning it on, and every inductor has a time constant that you plug into this equation. And that time constant is directly related to the inductance, just like we said it would be. So the bigger the inductance, the longer the turn-on time, the longer the turn-off time. But it's inversely related to the resistance in the circuit. So if you have a bigger resistance in the circuit, that turn-on time actually goes down. It decreases. Bigger resistance. Smaller resistance, the turn-on time goes up. And so this is what we call the time constant of an LR circuit, or an inductor resistor circuit. It's the time constant, and you use it in this equation to calculate how fast something turns on. For something that when you're turning off, you have to use another equation. It's a different function, but they're both exponential functions. The t in this equation is the amount of, and both of these times are in seconds, the t and the tau. The t in the circuit is the amount of time that you're actually, not the amount of time, but the actual time that you're actually measuring at. So this will tell you the current at a particular time, maybe 3 seconds after you turned it on, or 1 second after you turned it on. That time is the t. The tau is the time constant that you calculate from the inductance. So let's do an example really quick. We're going to have a resistor inductor circuit, And this resistor inductor circuit is going to have a 7.5 millihenry inductor in series with a 3 ohm resistor. Now it turns out it doesn't necessarily have to be in series, it can be in parallel as well, and the equations are the same. But in this case we're doing them in series. And we want to find the current 5 milliseconds after the switch is disconnected from the battery and connected to the other wire. And then they tell us the initial current is 10 amps. Now that initial current in the equation is I0. The final current at the time that you've specified is I. We want the turning off equation, which is this equation. But the first thing we need to do is calculate our time constant, which is the self-inductance over R. 7.5 millihenries for this inductor, 3 ohms for the resistor. So it's 2.5 milliseconds is the time constant for this particular LR circuit. We plug that tau into our equation with the time, which is 25 milliseconds or 0.025 seconds. Plug those things in, and we'll get that our final current is 0.368 times our initial current. So we take 0.368 times 10 amps, and we get 3.68 amps at 2.5 milliseconds. I thought they said 25 milliseconds. Oh, anyway. Oh, and 25 was here. But anyway, so we get our final current. Oh, so this is actually, why are they splitting it into 2.5? Oh, I see what they're doing. Here they're doing this a different way, which I actually don't like what they're doing. So at 3.68 amps, they're going to lose 0.368 of their current for every time constant, and the time constant was 2.5 milliseconds. So for 5 seconds, you would lose 0.368 amps of your original current, then another of your final current. But you could also just plug in your 5 milliseconds into this equation, which they didn't do, and they should have. They just said that you lose 0.368 amps of your current, or 0.368 of your original current after each time constant. That's kind of a, I think that's counterintuitive, but for most people, but anyway, that's fine. Just plug it into the equation, it works just fine. Okay. Now, let's talk about what happens in time. We've already seen in the last section that when we drive a current through this, when we connect this to a voltage, the current doesn't start up right away. There's a time lag. There's a time differential between the voltage and the current. The current starts off later. And this time lag is actually quite important when we're dealing with inductor circuits. So here's our voltage. Our voltage is going up and down here. It's the red, I think. Which one's the red, actually? I think the voltage is the green, actually. So the voltage starts out high, goes low, and then goes up and down. And then the current starts out later. So the voltage is high to begin with, but the current is just barely at 0, starting upward. So the current is essentially following the voltage. When the voltage is high, the current is low. When the current is high, the voltage is low. And so they're out of sync with each other. They're out of phase with each other. This has the overall effect of making the circuit look like the inductor is kind of like a resistor. It makes it look like the inductor is lowering the current most of the time. Because whenever you have a high voltage, your current is lower than it should be. So it's like the inductor kind of resists the current that's going through. This only is true in AC circuits, of course. In AC circuits, that's the only time when inductors affect the circuit at all. In a DC circuit, the inductors will not affect the circuit unless you're turning it on or turning it off. But in an AC circuit, it's always being turned on and off. It's always going back and forth, so it's always affecting the circuit. This so-called resistance that an inductor pretends to put into an AC circuit, we call it the reactance. And it behaves much like a resistance, but it is out of phase. It behaves like a resistor at a different time than a resistor would behave. we say that the current lags behind the voltage because as the voltage is building up, as the voltage is at its height and coming down actually, the current is just building up. So they say that the current lags behind the voltage when you have an inductor in the circuit. And to calculate the amount of current that goes through a circuit, we need to know how the inductor behaves like a resistor. So if we used Ohm's law with the reactance of an inductor instead of the resistance of a resistor, this is what it would look like. We would have the current in the circuit is equal to the voltage in the circuit divided by the reactance instead of the resistance. We use X sub L for the reactance of an inductor in a circuit. But what is X sub L supposed to be? Well, again, this is a little bit beyond this class, the mathematics of this class, but it turns out to be equal to 2 times pi times the self-inductance of the inductor times the frequency of the AC circuit. The frequency matters because how fast it moves determines how much the inductor has the opportunity to affect the circuit, right? Well, it determines how much the inductor affects the circuit. So the faster the frequency, the more the inductor affects the circuit, in other words. But it's still just Ohm's law. If you know the frequency of the AC current and you know the inductance of the inductor, then you can calculate the reactance or the resistance, quote unquote, of the inductor and determine how much it affects the circuit. So in this particular case, we're going to have an inductor that has a 3 millihenry self-inductance, and it's going to be in a 60 hertz circuit. And also, we're going to put it in a 60 hertz circuit and a 10 hertz circuit. And then we want to know what is the current at each frequency if you have 120 volts. Now everything has to be RMS in these cases. RMS meaning root mean squared. And so we plug in the numbers. We first calculate the reactance of this inductor at these frequencies. So at 60 hertz, it turns out to be 1.13 ohms. So at 60 hertz, this inductor behaves like a 1.3 ohm resistor. At 10 hertz, we have an inductance that is not 10 hertz, 10 kilohertz. So it's 10 kilohertz and 60 hertz. I'm like 10 hertz should be lower, but 10 kilohertz is much higher. So here we go. We multiply all those numbers together and we get 180 ohms, which is much higher than the 1.13 ohms. So at the higher frequency, the inductor affects the circuit much more, and that's what we expect. So now we are going to calculate the RMS current using Ohm's law, I equals V over R, which becomes I equals V over X. So the voltage 120 over the reactances, 106 amps we're going to get with the lower frequency, and then we get 0.637 amps at the higher frequency. Now this is kind of interesting. If you had a device like this if you had a device that was made from an inductor that is this size, it would let anything that was 60 hertz, it would let through with almost its full current. You started with 120 amps of current and you end up with 106 amps. That's most of the current would go through. But you can choke off the current at high frequencies using this inductor. Because the current goes from 120 amps to 0.637 amps, it's like the current didn't even go through. So inductors can be used to select currents. And this is the key to doing things like having a cell phone. Your cell phone only allows certain frequencies through, the frequency that your cell phone is on at that time. How does it do it? It uses an inductor at just the right value so that it only lets through a certain frequency. Now this one will allow anything below a certain frequency, and so it'll allow a bunch of frequencies through it. So we need to make this a little more complicated, it's a little more complex, so that we can allow just a narrow band of frequencies. We need to choke it off at one frequency. But we're starting to see this. We're starting to see the electronics that are used in stuff today. This is what we call this could be used as a pass filter. This would be called a low pass filter because it allows low frequencies to pass, allows the currents to go through when they're low frequencies, but the high frequencies it doesn't allow through. So this is what we call a low pass filter. What would we do for a high-pass filter? Well, we would use a different device. For example, a capacitor. Now, a capacitor behaves just the opposite of an inductor. When the voltage is high, the capacitor is accepting all that, wants all that stuff to come through. So you can see here that the current, instead of being up here, instead of going up, it goes down on a capacitor when the voltage is at its height here in this case. And so it's just the opposite of an inductor. So what an inductor does is it stores energy in a magnetic field, but it lags behind the voltage. With a capacitor sees that voltage right away, and it allows current to flow to it right away because the capacitor is empty, right? But eventually the capacitor gets full, and it doesn't allow any current to flow anymore, right? So it behaves just the opposite of an inductor. So it has just the opposite effect. For example, instead of allowing low frequencies to pass, capacitors will allow high frequencies to pass. And so we can actually start to choke things off with this. But this is also going to have a reactance in an AC circuit. You can put a capacitor in an AC circuit and it has a reactance like a resistor would have a resistance. But it's computed differently. Instead of being directly related to the frequency, as the frequency goes up, the reactance goes up. This one is inversely related to the frequency. As the frequency goes up, the reactance goes down. So it's 1 over 2 pi times the frequency times the capacitance. So in this case, we could use, we do the same problem that we just did between 60 hertz and 10 kilohertz with a 5 millifarad capacitor at 120 volts. We calculate the reactance first. Turns out to be 531 ohms at the low frequency, so it's really high reactance at the low frequency, but only 3.18 ohms at the high frequency. And this one, the current at the low frequency is 0.226 amps. It doesn't let anything through at low frequency, but at high frequency it allows almost all of the current through, or more of the current through. What if we use these together? Something that cuts off things at low frequencies, something that cuts off things at higher frequencies. We could narrow an area of frequencies that we let through if we use them together. And that's exactly what's used in your phone. Your phone has a variable capacitor and a variable inductor that can change. You can change those two things so that you can shift around which frequency you're going to let through. So your phone receives a phone call. The phone call tells the phone what frequency to choose. Your phone adjusts these capacitors and inductors to choose a frequency. And then it lets through just that frequency. The current that's coming through is allowed through. Everything else gets cut off.
Is that how radios work?
That's how radios work as well. You choose a particular channel. By turning that knob, you're adjusting these things. Right? With a radio, it's a little bit simpler. But you mostly with a radio, you're just going to adjust the capacitor to select the frequency. But with phones, you have to be a little more precise. So, and it's done by computer in your phone, so you can be more precise. In fact, I actually have somewhere. Here it is. Check this out. This is an adjustable capacitor from an old radio. The plates are here. Right, and when I turn this way, the plates go in between each other. That increases the capacitance. The more they overlap, the bigger the capacitor gets. The less they overlap, the smaller it gets until it's almost zero when it's out to here. Right? So this is an adjustable capacitor from an old radio when we used to use knobs to adjust the station on the radio. I love this thing because it's so easy to see what's going on there. I almost forgot I had that. Now, what does the resistor do? The resistor really doesn't change in an AC circuit. It just reacts to the current directly like it always has. And the only thing that a resistor really does is it adjusts how big the current is, because it directly affects everything. So the resistor will increase or decrease the amplitude of the current And that's pretty much what it does in an AC circuit. Oh yeah, I should probably show my capacitor on my camera up here. Good thinking. Here's my variable capacitor for the name of our student who watches this is Luke, just in case you're wondering. So here's my variable capacitor. You've got all these plates in here that are completely overlapped right now, but I can decrease their overlapping by turning the knob and letting the plates rotate out from the other plates. So this is from an old radio. Very cool little piece of ancient equipment. Okay, so now let's talk about what happens when we put all these three things together in a circuit. You've got a resistor, a capacitor, an inductor, and a circuit that's got a frequency back and forth, back and forth. Each one of these is going to affect the current in the circuit, but at different times during the motion of the change of the voltage. The voltage is changing all the time, and at one point when the voltage is high, the impedance through the inductor is really high, but at the other time when the voltage is really low, the impedance through the capacitor is really high. But all the time, the resistor is there. The resistor is always resisting all the time, doesn't really care what's going on with anything else. But these things work. They work against each other and with each other. So when the magnetic field is really high in the inductor, the electric field is really low in the capacitor. And back and forth and back and forth. Depending, well, not necessarily all the time, that's not always the case. But it depends on the frequency, it depends on the different values of the capacitor and the different value of the inductor. Because sometimes if you have a really big inductor, it takes longer for that inductor to fill up its magnetic field, and it takes less time for the capacitor or whatever else. So you can start changing things. And all these voltages can be really out of whack with each other. But if you just take it as an average all the time, you can still use Ohm's law. But you need to use all of these reactances or these resistances as one. You need to be able to express them as one. And that is where the impedance comes in. So the impedance of an AC circuit is a combination of the resistance of the circuit and the capacitive and inductive reactances of the circuit. But it's not as straightforward as you think. You can't just add them together. And the reason is actually deeply mathematical. It has to do with what we call phase space in physics and engineering. And again, it's a little bit beyond the math of this class, but suffice it to say that these add together like the sides of a right triangle. So it starts to look a little bit like, the Pythagorean theorem, where the total reactance or the total, what we call impedance of a system, is the square root of the sum of the squares of the resistance and the reactances. Except it's not the sum of the reactances, it's the difference. Because remember, the inductive and the capacitive reactances are opposites of each other. They behave differently at opposite times or at opposing times in the voltage of the whole circuit. So you take the inductive. It doesn't really matter which one you take the difference of, but you just take the difference between the inductive and capacitive reactances, you square that, you add it to the square of the resistance, you take the square root of all of that, and that's where the Pythagorean theorem comes in, and you get what we call the impedance of the circuit. So the impedance of the circuit is the overall resistance of an AC circuit. And we've got a great example of it right here on the desk. On this desk we've got our function generator, which creates AC currents. We used this in our lab yesterday where we created an AC current that was going through those coils, right? Let's put this up on my computer. Where did it go? There it is. And on the output that we plugged into it says right here the output is 50 ohms. Well, the output is not pure resistance because this is an AC circuit. And AC circuits always have reactance. They always have at least inductive reactance, but they also probably have capacitive reactance. There are all kinds of capacitors and inductors inside this thing in addition to resistors. And all kinds of loops of wire that aren't intended to be inductors but are anyway. So this has an overall inductance, and it's designed to have, an overall impedance, And they designed it specifically to have a particular impedance so that when you're using it with another instrument, you know what kind of resistance or impedance that this thing adds to the system. And that's the impedance of an AC circuit. And again, you can use this in Ohm's law. Ohm's law is V equals I times R, but in an AC circuit, you replace that R with Z, which is the impedance. So it's V equals I times Z. And again, here we have an example. We've got a 40 ohm resistor, a 3 millihenry inductor, and a 5 microfarad capacitor. And they want to know what is the impedance at 60 hertz and at 10,000 hertz. So again, we're going back to the same problem we did before. Two different frequencies. What is the impedance? The impedance is this long thing that we have to calculate, but we first have to calculate the two reactive capacitance and reactive inductance. Inductive reactance, there we go, and capacitive reactance. Calculate those first. We've already calculated them because they're the same values as the previous examples, so we know what those are. We can just plug them into this formula with our resistance, which is the 40 ohms, and we get 531 ohms at 60 hertz and 190 ohms at 10 kilohertz. So that's the overall impedance of the circuit. You can see that at the high frequencies, the let's see at the which one's the high frequency? Yeah, at the low frequency, the capacitive reactance is much larger, and at the higher frequency, the inductive reactance is much bigger. So those are the things that kind of take precedence. They make the biggest difference at those different frequencies. Now, what does this all mean? In the end, when we use this together in Ohm's law, it looks like this, where we have current equals voltage over impedance here. Now, the impedance down here has a difference in it, right? And this current, I, is going to be dependent on this difference. If this difference down here is big, then the entire impedance is going to be big and the current is going to be low, right? If the impedance down here, if either one of these numbers, if this difference is big down here, if either one of these numbers is much bigger than the other, then we're going to have a big resistance down here or a big impedance, and that's going to be, we're going to have a number over a big number and we're going to get a small current. If we want a big current, this has to go away. In other words, our inductive reactance and our capacitive reactance have to be equal to each other. If they're equal to each other, then this part goes to zero, or our resistance is the only thing in our impedance, and our impedance goes to a minimum and our current gets big. And that's ideal. If we can make that happen, then we will get the biggest current out as possible. And that's what we call the resonance of the circuit. And that happens at a specific frequency. If you pick just the right frequency for any inductor and capacitor in an RLC circuit, you can actually make your current become maximum. And that frequency is what we call the resonant frequency. And it's equal to 1 over 2 pi times the square root of the inductance times the capacitance. So for any given RLC circuit that has a resistor, inductor, capacitor, you have a frequency that it resonates at, that it builds up a highest current. And that's exactly how we make cell phones. That's exactly how we make radios. Everything else, we make them so that you can tune into a resonant frequency, so that you can make this gap just narrow enough to just pinpoint this particular frequency and amplify it. So here we have an example with the 40 ohm resistor, the 3 millihenry inductor, the 5 microfarad capacitor. We find the resonant frequency by just plugging them in. Turns out to be 1.3 kilohertz. If you drive a 1.3 kilohertz AC current through this thing, it will create a huge current in the circuit. The current will go up to its maximum because essentially your inductance and your inductive reactance or your capacitive reactance cancel each other out. So you get a huge current. Now, how is that really all that valuable? Your cell phone does not have an AC thing that drives a current through the phone. What it has is an antenna that picks up a wave that's going through the air. That wave that's going through the air goes into the antenna and creates an AC current in your antenna. The antenna is connected to an RLC circuit that will amplify that AC current coming from the airwaves if it's the right frequency. If it's the right frequency, you'll get a big current coming through and you'll be able to hear the voice of the person you're talking to. If it's not the resonant frequency, you will not get a big current. And you will not hear the voice of the person. So phone calls that are not the right frequency, you won't hear. Phone calls that are the right frequency, you will hear. And you can adjust that frequency by adjusting the inductor or capacitor, or both. Now, how much current are you going to get through? This is called the power factor, and they calculate the power factor using what is called the phase angle between the voltage and the current. So they use this equation here, and the phase angle is something that they will just give you in this case. I'm not going to go through that really quick because we got to move on. We got to get through this. Are we done yet? Can't remember if we have one more section or not.
Can you explain that again real quick? So our cell phones have an antenna, and the antenna has
Oh,
a
we're done.
specific frequency.
Yeah, and let's take a look at that really quick. If you need to go, you can, but we'll talk about this really quick. We'll use a let's use a applet to describe this. So here's an RLC circuit. And let's see what they've, no, this is not the one I want to do actually. Let's look at one that is more like an antenna. They used to have a really good one. I'm not seeing it here anymore. Let's go back to our RLC applet. This one is not a bad one. Let's see if we can. Yep, that's not working for us. All right, we'll go back to the other one. We'll make the other one work. It's not going to help us. This one, right? Okay. All right. So anyway, here is our LRC circuit. You have the inductor, resistor, capacitor right here. The problem with this circuit is it doesn't have a source. They're not showing us the source that's causing this. The way to create the antenna is to cut the circuit right here and put your antenna on either side of this. So that when a wave comes by through the air, it causes this one side of the antenna and the other side of the antenna. It causes the electrons in those antennas to go up and down. And then it drives those electrons back and forth through the rest of the circuit. Okay? So that's what an antenna would look like. It would look like cutting this right here and just pointing it off into space and letting that be the source of your current. So the electric field that is from the radio wave can actually cause the electrons to go back and forth in your antenna. As they go back and forth in your antenna, they see these capacitors and inductors. But depending on the frequency of the wave that is causing the electrons to move, that will determine how much this gets moved. Okay? For a frequency that's not quite right, this is what you'll get, right? What you're seeing right now, not much movement. And not much movement means you won't hear anything because there will be no current to drive the speaker in your phone. However, if we get just the right amount of movement, just the right frequency, so that when this thing is at its maximum, this one is also at its maximum and they're equal. So yeah, essentially what you're getting is a better way of thinking it is that that these things kind of push and pull the circuit at different times. And if when this one is pulling this way, this one is pushing this way, they're going to cause this circuit to really get a lot of current, right? If they're kind of in sync with each other, pushing and pulling, then you can get a maximum amount of current. But that can only happen if we can get these things in the right with the right frequency. The frequency has to be correct, or the size of them has to be correct. So we adjust the size to correspond with a particular frequency, and then we go out there and look with that frequency. And then you get, let's see if we can, let's see if we can change the, see this one, the frequency is at a particular frequency that we can't change. So if I can change this, then you get a lot of current if you can get it at just the right speed. I haven't got it quite at the right speed yet, or quite at the right frequency. But if you can get it there, it will really max out. It will really peak out is what happens. So let's I wish that they actually had this connected to an RC, to a, let's see if I can change something here. Don't think I can. Oh yeah, I can. So let's add an input. See if they have an antenna. Yeah, they have an antenna right here. So let's add an antenna right here. Antenna. And let's actually can we take this out? Let's cut that out. So here's my antenna, and let's add in a an FM source. Draw a add an FM source right here. Oh, do they have to add it into this? Okay, that's fine. Oops. That's not exactly how I want to do it, I don't think. Let's start, let's see what happens here. Okay, so you can kind of see what's going on here. We've created an AM source, but we don't have, obviously we're not getting resonance because it's not creating a lot of current, right? So we need to change our AM source. Let's change the frequency here really quick and see what it does for us. See if it changes the see if it changes our current. Apply. Change it. Let's go to 100. Let's apply. Let's go to 1,000. Let's go to 1,000. Oops. About 1,000. Apply that. Now we're starting to get more current. See that current? So now we're closer to the frequency that this circuit is designed to resonate with. So as this AM source is creating this wave that's going into these antennas, it's causing this resonance to go back and forth. Okay? But at those lower frequencies that we had, it wasn't causing the resonance. And you can see it's dying off a little bit here, and it will build up again eventually. But because we're not exactly at the right frequency. To know the exact frequency, we'd have to calculate it using our 1 Henry inductor and our 15 microfarad. And we could do that. We could use in our 10 ohm resistor. We could plug that into our equation for the frequency and calculate that frequency and plug in the exact frequency. Let's do it actually. 15 microfarads times 1 Henry. We go back to our book. Where's our book? And the resonant frequency, if we go back here, is 2 times pi time, let's see, what was it? Resonance right here. Its resonant frequency is 1 over 2 times pi times the square root of L times C. So let's see, do I have a calculator here? Not really. Let's see. I don't have square root here. Can somebody do that calculation? I don't have a good calculator for that. We need we need the square root of 1 times 15 microfarads. Actually, I'll just make this 1 here. I'll edit, let's see, I'll edit the capacitor, and I'll make it 1 farad. Apply that. Okay. So now it's 1, so it's over square root of 1, so it's 1 over 2 pi. So we've got 1 over 2 pi, which is 1 over 6, right? So our resonant frequency is 1/6. Our resonant frequency needs to be 0.15-ish. So I'll change that really quick. Frequency, I'll make 0.15. Apply that. And now we're seeing a huge rise in current, right? Which is what we should get.
So now that we matched up our frequency, that's when we'll be able to hear.
Yeah, that one. Once the frequency is correct, you get this huge current flowing, and that huge current can drive a speaker, so that you can hear something. Right? So that's kind of the idea there. That's definitely the idea of the resonant frequency. All right. So that is that. Have a good day. I'll stop my recording now.